Hello, and welcome to the first video accompanying Lecture 29. In this video, we're going to cover Section 13.4, which is on the topic of the motion of satellites, and this is from Young, 14th edition. Okay, so we have a couple of objectives in this section as we continue our discussion of gravity, and that's to understand that the motion of satellites can be understood through the conservation of energy using universal gravitation, which we talked about in the last lecture, universal gravitational potential energy, that is, combined with uniform circular motion and the associated centripetal acceleration used with Newton's second law. We also want to realize that elliptical orbits can be approached through similar techniques. Okay? So, I think we all know what a satellite is, but I want to talk briefly about the definition. So we could say that a satellite can be natural or artificial or natural. So an object that is natural, that'd be like the moon, or artificial, like a communication satellite that is in orbit around a celestial body, like the Earth. You can orbit moons as well. Okay, there are satellites of the moon. All right, so these are artificial objects that have been placed in orbit around the moon. All right. Satellite orbits can be circular or elliptical. Okay. If you're not that familiar with ellipses, a circle is a form of an ellipse. It's just an ellipse with an eccentricity of 0. We'll talk a bit more about ellipses, although we don't get too much into the topic, largely by my own choice. I think there's other things I want us to focus on. But we will talk about them briefly, and we'll talk about some of the key terms and ways of quantifying an ellipse, including eccentricity. An important idea about satellites is that satellites have to have a large enough velocity and thus kinetic energy so that they never hit the ground. So satellites must have a large enough velocity, and we'll say so that they can complete a curved trajectory around a world. Or celestial body, as I said before. Okay, a general term for a planet or a moon or something like that. Okay, so the idea there is a fun one. You can imagine building a tower that is 100 kilometers tall and then throwing a rock off the top of that tower. At 100 kilometers, you'd have very little atmosphere, so very little drag. Of course, as it fell, the rock would pick up drag as it fell into the atmosphere. But if you threw the rock at a low speed, it would take a fairly parabolic path. It wouldn't be a perfectly parabolic path because the acceleration would not be constant. As we know, the acceleration would vary with the distance, especially at such a high height as 100 kilometers is your starting height. But if you imagine throwing that rock faster and faster, your curved trajectory, okay, not parabolic, but still curved, would get larger and larger. It would cover more and more distance, lateral distance, before the rock hit the ground on the Earth below, far below. And if you threw it so fast that it was falling a certain amount as it moved to the side, so that its vertical displacement was very small for a very large horizontal displacement, then that curve could match the curvature of the Earth below you. And in that case, your rock would never hit the ground, and you'd have yourself a satellite. Okay? So that's what satellites are. They're just going so fast that although they're falling, they never hit the ground. All right? And that curvature of the Earth is about 5 meters per 1,000 meters. Okay? So you fall off 5 meters per every 1,000 meters. As long as you have that curvature, then you would never hit the ground. Now that 5 meters per 1,000 meters would be if you had a satellite that was like at sea level. Of course, that would present all kinds of problems like crashing into mountains. And first of all, have to be way too fast because you'd be in the atmosphere and you'd burn up at that speed. Okay? But that's a good kind of rule of thumb of thinking about what curvature means, even though that 5 meter drop per 1,000 wouldn't apply to the larger radii orbits that we'll be discussing. All right? Although some of those low Earth orbits aren't particularly large, so it'd probably be still pretty accurate. Okay, so you probably had a good idea of a satellite. Maybe you had never thought of it as an object that's falling, but just moving to the side really fast so it never hits the ground. I think that's a very useful way of thinking about it. So let's move on to the key equations, and let's discuss the potential energy of satellites, a little bit about the sum of forces on those satellites, relate that to the kinetic energy, and then finally bring it all together to the total energy of the satellite. Okay? So we're going to use kind of a combination of the energy approach that we were looking at for, say, escape velocities or just launching objects straight up in the previous section of this chapter, and then combining that with centripetal motion because we want to create a circular orbit. Now, you might be wondering, what about ellipses? Well, we're going to set the stage with circular orbits. That's really going to be most of the examples. If we want to do an ellipse, we do a modification, and I'll show you an example of that. Okay? All right, so this first equation here, this one, is just the potential energy of a satellite. That would be the same as the potential energy of anything that's at a height r. Okay? So let's go ahead and label this. So this wouldn't necessarily be a satellite, in other words. You know, if I just had an object at rest at a distance r from the center of the celestial body, then that object would have the same potential energy. Of course, satellites are not at rest. Otherwise, they wouldn't be in orbit. They would just fall straight down. They have to be in motion, right? It's negative because satellites are still within the gravitational well of the celestial body that they are orbiting. M is the mass of the world. I'm just going to use the term world here and drop celestial body because it's shorter. So m of world, or say mass of world. Okay, and then I'm using lowercase m for the mass of the satellite. All right, r is the radius of the orbit of the satellite. And importantly, r would equal the radius of the world plus the altitude, that's the height above the ground, of the satellite. Okay? So this is world radius and then height for altitude. Okay? Now, sometimes it's not a big difference. Think 300 kilometers or 330 kilometers or something for low Earth orbit. You add that to 6,000 kilometers. That's a appreciable percent difference, but it's not giant. But certainly, if you had a satellite that was 3 Earth radii above the surface of the Earth, then your little r is a lot bigger than your big R. Okay. All right. So there's our energy. Definitely refer to the previous lecture for review of that topic. So then the forces, all right? So if we imagine our world, all right, like so. So some circular planet. Let's give it a radius of big R. Okay. And then we'll have our satellite at a height of little r. And then the orbit will look something like this. Kind of line that up. Close enough, right? All right, so then that's our satellite orbit. If we then were to draw our satellite as a little rectangle up here, so something like this, we could then think of the sum of forces acting on that satellite. So we'd have a gravitational force, all right, and that's it, okay? That is the only force acting on the satellite. just a single force, a single external force acting on the satellite. Now the satellite's not at rest, it is undergoing acceleration, and the type of acceleration it's undergoing, if we, again, start thinking it as a circle, would be exactly centripetal acceleration. Okay, so our FG right there is exactly universal constant of gravity times big M, little m, over the distance from the center of the world to the location of the satellite squared, because this is the universal law of gravitation. Okay, this is the force equation that we introduced 2 lectures back. All right, now that single external force, because that's your F net, just one force, is equal to ma. And of course, A is centripetal acceleration here. Centripetal acceleration. Okay, so then let's go ahead and solve for V. Okay, so then we can say from F net on the satellite, we would have V squared would equal, we cross multiply it by R, so then we just have, and we divide both sides by M, which would cancel. So we'd have G M over R. Okay? And, okay, so take a look at that. That's your V squared, right? If I wanted to solve for V, obviously just take the square root of both sides. Okay, which I have there. Okay, so I'm just actually going to draw 2 arrows from this. So we'd have one arrow that would go down to just solving for V, like this. Okay, so I just solve for the velocity of the satellite. That would be true for any satellite. Okay, so the velocity is really fixed on how high that satellite is. So if I have a satellite that has an H, an altitude of 1,000 kilometers, then I'd add Earth's radius plus that 1,000 kilometers. That would give me my R, so about 7,300 kilometers. 6,300 for the radius of Earth, plus the 1,000 for the altitude, 7,300 total. Okay, and then that would fix the velocity, right? So for Earth, any satellite at that altitude would have to have that satellite velocity to be in a stable circular orbit. Now you could have different velocities if you were in some sort of elliptical orbit, okay? More on that later. But if you were in a circular orbit, or an approximation of a circular orbit, then that's going to be your velocity. It's fixed, it's set. You know, if you want a different velocity, you better choose a different altitude, okay? Or the altitude, you know, sets the velocity. Now, what about the kinetic energy? Well, similarly, we know that kinetic energy is just 1/2 mv squared, so we could just take that v squared, multiply it by 1/2 little m for the satellite, and that just get us right back to the kinetic energy. Because, of course, K is just 1/2 mv squared. Okay? So, this is a neat result, right? We see then that the kinetic energy of the satellite is just gravitational constant, mass of the world, mass of the satellite, over 2 times the radius of the orbit. Okay? And then we can take total energy, which is just adding them together. Okay? Because what does that look like? Well, the total energy ends up still being negative. But of course it does. Okay, I mean, that's a neat idea, right? And if you can confidently be like, oh yeah, of course it does, then you really have understood the idea of gravitational potential energy and the idea of a gravitational potential energy well. Because a satellite's still in that well. If its total energy was 0, then it would have just enough kinetic energy to have escaped the well, and you'd have an escaped object. You know, that'd be like a Voyager probe, right? Sent out of not just Earth's orbit, but the sun's orbit, okay? Or I guess a lot of probes that are sent to outer planets in the solar system, like Cassini or something, right? New Horizons. You know, these are going to be satellites that have escape velocity greater than that of Earth. Now, many of them would have an escape velocity greater than velocity greater than the escape velocity of Earth, and then some leftover. So their total energy would actually not just be 0, because they're not just minimum energy to escape, but enough to have some leftover velocity so they can be coasting along rather than effectively just coming to rest at the edge of the solar system or something. Okay, if we consider that where Earth's gravity becomes negligible, besides all the flybys of planets, which complicates things. Okay, now thing is though, a satellite is none of that, right? A satellite's relatively close to Earth. It's still very much beholden to Earth's gravitational energy, and thus its total energy is definitely still negative. Okay, all right. And you can see where the numbers come from, right? Because this value right here is 1/2 of that value. So when you add 1 plus negative 1/2, you get, or excuse me, when you add negative 1 plus positive 1/2, you get negative 1/2, right? That's what we've done, right? This is our positive 1/2, this is our negative 1, and so then we're left with negative 1/2. Neat, right? Okay. So the total energy of the satellite is negative. Okay? Now, what about for ellipses? Well, it turns out for the ellipse, all you have to do is change over to replace your radius with the semi-major axis. Okay? So that's the change here. And we'll talk a bit more, as I said before, about the terminology for ellipses in the next video and next section. Okay, called Kepler's laws. So A is the semi-major axis of elliptical orbit. And you take, everything, because the whole thing, right? Like that, it's like I said before, circles or ellipses just with the eccentricity of 0. It's kind of like squares or rectangles, right? But just with equal length sides. It's the bigger categories, the rectangle or the ellipse. And a planet like Earth, in its orbit around the sun, right? Because of course the Earth is a satellite of the sun, is pretty darn circular, right? So it's very low eccentricity. And so in that case, we often can approximate A as R, right? So we can kind of be like, it's going to be close enough. Right? Same with the moon, orbiting Earth, okay? Our natural satellite. Okay. So the last thing I wanted to show you was the period of a satellite, okay? And this would be for a circular satellite. The reason I want to show you a period of a circular satellite is because we're going to talk about Kepler's third law, which is a famous law that relates periods to semi-major axes. And I want to show that actually is totally consistent with relating periods of circular orbits to radii of the circular orbits. So we're not kind of seeing that. I don't want that to be a disjointed transition. I want us to clearly see. And I'm actually, in one of the examples I'm going to show you in just a minute, the last example I'm going to show you in this video, I am going to refer to Kepler's laws a little preemptively before I actually lecture on it, just to kind of wrap up the problem and use it for the solution. But of course, watch the video on Kepler's laws, which is entirely just the explanation of the laws with no examples, because you're only responsible for a conceptual understanding of them. Okay. Other than when they come up in little parts of larger problems. So let's show you that period. So the period of a satellite and this could have been an example, I suppose, but I'm just going to kind of show it down here as a little derivation. So period of a satellite in a circular orbit okay. So how would we come up with that? Well, we'd want to relate V to just distance over time, okay? So we'll say from uniform circular motion we have that V is 2 pi r, that's the radius of the orbit, not the radius of the world, divided by t. Okay, so it's distance over time. And then we know that V is also equal from the sum of forces is equal to g m over r. All right? So then it's just a matter of solving for the period. So we want to go ahead and square both sides. So then I'm going to have 2p squared r squared divided by t squared is going to be g m over r. So notice that the period is turning out to be independent of the mass of the satellite. That's as it should be, just like its velocity should be independent of its mass. Okay, the forces tell us that. Newton's second law tells us that. Okay, and so then I'm just going to solve for t. So then I'm going to go ahead and cross multiply. So I'll end up with an r cubed. Okay, so I'll put my t squared over here. And then I want us to imagine that I have cross multiplied both sides by t squared, cross divided by gm, multiplied by r cubed. Okay, so I'll go ahead and write that as 4 pi squared, and then r cubed all over gm. Oops. Okay, did I do that correctly? I think so, right? Yeah, okay. And then I would just take the square root of both sides. Okay. Now, right away, if we look here, we can see we kind of have this nice relationship, right? We have that t squared is proportional to the radius of the circular orbit cubed. And you'll see in the next video that that's basically what Kepler's third law tells us, that there's a proportionality between the square of the period and the radius cubed. Okay? And it turns out that that proportionality is exactly 4 pi squared over universal constant of gravity times the mass of the world that is being orbited. Okay? And so that, so that's a nice relationship. In fact, let's even write it in that form by pulling the r cubed over here. And then, of course, if we wanted to actually solve for t squared, that wouldn't be particularly difficult or anything. We just would clean that up a bit. So then t is just going to be the square root of all this. 4 pi squared r cubed over gm. Okay, so that's always true, right? So again, just like all you needed to know to find the velocity of the satellite was its radius and the mass of the thing that's being orbited. Likewise, all you need to find the period of the satellite is the radius of the orbit and the mass of the world. Because you know g, right? That's a constant in the universe. Okay? And this, again, is the proportionality. All right? Cool, right? Okay. So let's do a couple examples. All right. So a geosynchronous satellite is one that stays above a fixed point above the surface of a planet. These types of satellites are important for communication networks. However, for planets with very slow axial rotation a long day, they may present a problem. What altitude would a geosynchronous satellite need to be located at above the surface of Venus's equator? Okay, so let's go ahead and just kind of just straight solve for this value and then kind of see if it does present a problem, because I kind of hinted at it might, and I haven't checked these numbers, but I think it certainly could, because Venus has a remarkably long day. Right, Venus's day is about as long as its year. Okay, that'd be like if we basically face the sun for half the year and then we're completely dark for the other half of the year. It's kind of unimaginable, right? But Venus is a strange world in many respects. Okay, so let's go ahead and just approach this, right? Just find the necessary period and all of that. Okay. Now, I've chosen this example because I wanted to do a couple examples in this lecture video that were similar to things that you're going to see in the lab. So I had posted a lab, which is a worksheet that has a bunch of practice problems, which are, I think, ones I've definitely kind of picked out as good examples, and I think they're quite valuable to solve. But I wanted to show you a couple so that you can maybe kind of see some processes if you're not sure on how to solve some of those problems. Okay, and so that's going to be true in the next example that I do. I'm going to do 2 examples in this video. All right, so, and that's lab 13, by the way, the gravity worksheet. Okay, so the idea of geosynchronous. Well, geosynchronous means that the period of the satellite matches the period of the day. Okay? That's okay. That's kind of the way to interpret that information. So it means that the period of the satellite matches the period of the day. Okay? And the reason is because if you think about it, that means that the satellite will take a certain amount of time to go all the way around its orbit, and the Earth below would take the exact same amount of time, well, that's where the synchronous part comes in. Because another term for geosynchronous is geostationary. Now, they have to be along the equator. I can let you think about why that is. But that means that you could have a satellite above the equator of Earth, for example, that is exactly above some location along the equator. Maybe there's some city on the equator, and that satellite would just sit above that city. It would never move. Okay? That's totally different than a satellite like the International Space Station, which has a period of 90 minutes. Well, 90 minutes is a lot shorter than an Earth day of 24 hours, isn't it? So that means that the International Space Station is going over all different parts of the Earth. Okay? But geosynchronous, also known as geostationary satellites, don't. They remain above a fixed location because of the matching periods. All right. So that's what we're going to do here. We're going to match our periods. Okay? So I'm just going to go ahead and take what we already know about the period. So we already know that the period, I'll say, from sum of forces of F net, so I'm going to say a bit more, I guess, G, M, and this would be MV, M, over R squared equals M, V squared over R, and V equals 2 pi R over TS for satellite, all right? And this would be TV, a T day, of course, is TV, so I'm actually going to relabel that subscript, because it's the period of the day of Venus, okay? Right, so that's our TS. And then we know that we just want our TS to be our TV, and then we should just be able to solve for the velocity, okay? So let's think about this, right? So, I mean, I can go ahead and just write it, write what we saw before, what I showed you on the previous page. So I know then that the period then is going to be the square root of 4 pi squared R cubed over GMV. Okay? Because the little m cancel out. We can show that here. Right? So the mass of satellite is going to have no bearing on the problem whatsoever. Okay? Now, that's great. But we're not solving for the period. We're setting the period equal to something, and then we're going to probably want to solve for R, right? Because we've eliminated V, so we don't care about the velocity. We literally just want to solve for R, right? So then we're just going to solve for R. And of course, we could have gone about it differently, but I wanted to sort of refer back to what I'd just shown you. So solve for the radius of the orbit. Okay. And so this will be with, I'll call this TS, but here I'll say with TS equaling TV, so the period of the satellite equaling the period of Venus. It's a very, very long day period. Okay. And all right, so then what is that going to be? So then I'd have my 4 pi squared R cubed over G mass of Venus equaling the period of Venus squared, because I've just squared both sides. And then we'll go ahead and just solve for R. So then R is going to equal TV G MV divided by 4 pi squared inside the cube root. Okay, so cube root. All right, so let's plug in our numbers. So I've got my period of 10.09 times 10 to the 9 seconds. 10.09 times 10 to the 9 seconds. Okay, and just to put that in perspective, that is, let's see, so if I take 10.09 times 10, oh, I meant to the 6. And I saw 6, but I wrote 9. So fix that. So 10 to the 6. All right, so 10 to the 6. And then we'll divide that by 3,600 to get seconds in an Earth hour times 24, just to compare this to Earth days. All right, so that ends up being almost 117 Earth days. That's one Venus day. Okay, that's what I mean about it being really, really long. Okay, and then we're going to put in our gravitational constant. Okay, so our 6.626 times 10 to the negative 11 Newton squared, meter squared, per kilogram squared. All right. Let's pull something up. All right. So 6.67. Oh, when I said 626, I was thinking Planck's constant. Yeah, I knew I was misspeaking. 6.67 times 10, which is a very, very different constant, especially on order of magnitudes, 10 to the negative 34 in different units. But sometimes the numbers are similar enough that I mix them up. Okay, so there's our universal gravitational constant. All right, and then we'll multiply by the mass of Venus, which is pretty similar to the mass of Earth. So 4.867. 4.867 times 10 to the 24 kilograms. Okay. And then 4 pi squared. And let's put this where I need it. All right, there. That's good. All right, and then I'm going to raise it all to the 1/3 power, just so I have it in a form that looks like what I'd be entering in the calculator. And I got plenty of space for this, so I'm not trying to squeeze it in at all. Okay, so 10.09 times 10 to the 6. Okay, times 6.67 times 10 to the negative 11 times 4.867 times 10 to the 24. Okay, divided by 4 pi squared, all raised to the 1/3 power. Okay, so we get 4.36 times 10 to the 6. So, why did I anticipate this might be a problem? Well, let's first see. Let's look here. So I gave you, we haven't used it, but I gave you the radius of Venus, 6.05 times 10 to the 6. Hold on. Our orbital radius is less than the radius of Venus. And whoa, that's really, really not going to work, right? So R is less than the radius of Venus. So this is impossible. So besides the other habitability issues of having a really long day, right, you also wouldn't be able to set up a communication network very easily because you couldn't have geosynchronous satellites to be in a known location relative to, cities on the ground, and then be able to bounce signals off of them. Okay, so that's a great thing about them. We always know where they are. Okay, so yeah, doesn't work. You cannot. Venus does not support geosynchronous satellites. It just has too long of a day. And again, to reiterate the idea, that's because you have, in order to have the satellite moving that slowly, right? In order to have the satellite moving that slowly, it would have to have that. It would have to have that radius that is very, there's very, very tight in. Okay, and so it just doesn't work out computationally. If we kind of what's the case in point here? All right, so let's see. So we have So I just want to see if there's anything else I want to say. I mean, if we consider plugging in a period that is, that's going to give you a very different number, right? That's going to give you the radius for geosynchronous satellites for Earth. Let's see. I feel like that might be a good and important comparison. So I mean, just speak to it. I'm not going to write anything down, especially because that is one of the problems in the lab that I'd like you to definitely attempt those problems on your own. But just for kind of conversation here, mention it. So our geosynchronous satellite, and this is number 6 from the worksheet, we end up with a value of much, much greater than the radius of Earth. It ends up being like almost 6 times greater than the radius of the Earth. Okay, and so, but where is that coming from, right? Well, it's coming from the fact that what's the way to put this? We need the velocity to be fairly fast, right? So, because the velocity doesn't match the velocity of the surface of Earth, and that's it. That's an important thing, right? Because if the velocities matched, they would only be synchronous if they had the same trajectory, but they don't. The orbit is much, much larger if you have a functioning geosynchronous orbit than the circumference of the planet that you're synchronizing with. And so, for comparison, that's a person standing on the equator of the Earth is moving about 250 meters per second. A geosynchronous satellite in a geosynchronous orbit around Earth is moving at about 3,000 meters per second. Now, that's actually fairly slow for an Earth satellite, but it does allow it to have an equal period. It's just kind of neat, right? Totally different velocities, but equal period. But the idea is that you need to have, you need to actually have that radius that works, right? Obviously it needs to be greater than that of the planet. And so, let's see. Oh, I see what I did wrong though. Okay, so I just caught a mistake in this solution, which is kind of why if maybe I was buying myself a bit of time there, because the numbers weren't working out. So let's see. Here we go. Of course, what I forgot to do was keep that squared. That was a big mistake. Okay, so let's fix that. So it may work out. Let's see, because we're actually going to have. So I think the issue isn't so much that it's going to be less than the radius of Venus. It's that it's going to be so large, because the proportionality here is that the orbital radius of a geosynchronous satellite for any world goes up with a proportional to t to the 2/3 power, right? So as t gets bigger, r should also get bigger. So it definitely shouldn't be smaller than the radius. I think perhaps the problem here is that it's going to be so big that it might be too far away. Okay, so let's go ahead and fix those numbers with the correct thing. Squaring a million is a big deal. So let's do that. So sorry for the mistake, but if you were watching the video and wondering if I was going to catch the mistake, I certainly have. So let's do that. There we go. So 9.42 times 10 to the 8. Good. Okay, yeah. Okay, so 9.42 times 10 to the 8. So you'd only have this issue about your geosynchronous orbital radius being less than your world radius if you had a very, very fast world. If you had a world that had a really, really short day. So probably the examples of that would be to find a gas giant that's spinning very, very quickly. That'd be a good example in the future. I'll have to work on that, or just plug in the numbers and see if it works. Okay, so that means that the height. So we can say thus, the height above the surface of Venus is then going to be r minus rv. Okay, so let's do that. So I'll take my 9.42 times 10 to the 8 meters, and then we'll go ahead and subtract out the radius of Venus. So 6.052 times 10 to the 6, yeah. Okay. And again, just 300 kilometers smaller than the radius of Earth. Venus is really like Earth's twin, but where things went very differently. Okay, but it's a different distance from the sun, which has a big effect. Okay, but that day doesn't help, potentially. A lot of different theories about all the strange behavior of Venus. It's a whole deep dive we can't get into. Okay, so 6.052 times 10 to the 6. All right, so then we get 9.36 times 10 to the 8 meters, okay? And then let's find out how many Venus radii that is. So I'm going to divide that height by 6.052 times 10 to the 6. Okay, and this should say 6, of course. Okay, so we end up with about 155 Venus radii. Okay, whereas I said Earth's is about 6. That's pretty far for a satellite. I mean, the moon is 60 Earth radii away. So this would be a satellite that is not 3 times, but over twice as far as Earth's moon is from Earth. That's pretty far for an artificial satellite. Would that make sense? Would you really want to would you want to have a satellite that far away? And lastly, let's see how fast it's going, right? So what would be the velocity of this satellite? Now, there's a couple ways we could solve this, right? We could just obviously I can just plug it back in and just solve for the square root of gm over r. Another thing is I could just take the radius that I now know, right? Because I know the radius of its orbit, and just do 2 pi r over t, because, so I'll do it that way, because I think that's probably maybe not the way you necessarily think of it. You might go back to the equation. It's good to see, how these all fit together. Okay, so I'll write both of them. So it'd be gm over the square root of gm over r. Mass of Venus over r. Okay, or it's just going to be 2 pi r over the period. Okay, which is both the period of Venus' day and the period of satellite. All right, so what does that give us? So 2 pi times 9.42 times 10 to the 8. And I'll just make a note here that this is perhaps too far. All right, and then we'll go ahead and divide by our, 10.09 times 10 to the 6 seconds. All right, and that will give us our velocity. Okay, so let's see what we get. 2 pi times our orbital radius by 10.09 times 10 to the 6 period. All right, so 583 meters per second. Yeah, very, very slow for a satellite. Maybe still manageable, could you even get it going that slow? And because I was thinking if it's too slow, if it's just a few meters per second, then that would present some other problems too, because it doesn't have a lot of kinetic energy at that point. And if you don't have a lot of kinetic energy, then it'd be really easy to get pushed off course by even small perturbations. And so there might still be an issue here, because as you start to kind of lower and lower that kinetic energy, you start to get something's going to come. What happens when there's a conjunction between worlds or something, right? All of a sudden your orbit's all out of whack, right? Although I suppose it would take very little fuel on board to adjust the orbit back to where you needed it, because there's it'd be. Although on the flip side though, you'd have to do tiny thrusts, because if even a small thrust would push you way off, because your kinetic energy is pretty small. But again, here 583, that's probably not tiny kinetic energy, so it might still be manageable. Okay, so small kinetic energy for satellite. But there might be some benefits of that, right? Like I said, maybe you could have very little fuel on board, or just do all your adjustments for perturbations with solar energy. Okay, so again, hopefully interesting, even though I know I meandered off the path there a little bit. Okay, so I want to show you one other example. I'll try to keep it tighter. So I'm going to leave 2 and 3 for practice, but I want to show you example 4, which is similar to problem 7 from the study guide, or from the lab worksheet. Okay, so let's take a look in a shuttlecraft. Okay, So, first of all, we're going to just kind of jump into this. So, in a shuttlecraft of a certain mass, 300 kilograms, Captain Jane orbits a planet of big M, 9.5 times 10 to the 25 kilograms, so about 10 times bigger than Earth, in a circular orbit of radius 4.2 times 10 to the 7 meters. What are the period of the orbit and the speed of the shuttlecraft? Okay, well, we can do that pretty easily. All right, so I'm not going to rederive any of this. We know that the period is just going to be the square root of 4 pi squared over over gm times r cubed. All right, and then that works out to be, plug in all the numbers. All right, so 4 pi squared times our radius of 4.2 times 10 to the 7 meters squared. All right, oops, again. All right, there we go. There we are. And then 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. All right, and then our mass, which was 9.5 times 10 to the 25 kilograms. All right, looks good. Okay, so we'll plug in those numbers, and we get 2.15 times 10 to the 4 seconds. Okay, so there's our period. That's part A. All right. Now, but in part B, all right, the speed. All right, so we know how to do this. So the speed is just going to be 2 pi r over the period, which we just solved for. All right, so it's just going to be 2 pi times 4.2 times 10 to the 7 meters divided by 2.15 times 10 to the 4 seconds. All right, and so that's going to give us 1.23 times 10 to the 4 meters per second. Okay, this one's fast. Now, part of the reason is it's because it's a bigger world, right? So having that extra mass has a big effect. Because here we're going 12 kilometers per second. That's about twice as fast as the fastest satellites orbiting Earth, okay? Which are going about 6 kilometers per second. Here we're going 12 kilometers per second. Okay, so now let's see some new stuff. So just then, the speed is going to be reduced by 2%. So if I was a forward-pointing thruster, kind of pushing her back, right? And there I call it Janeway, like from Star Trek, right? So pushed back by 2%. Just then, what are the speed and the kinetic energy? Okay, so let's do that. So if we're going to reduce the speed by 2%, well, that's just going to be, so we'll call this V final is going to be 90.98 times V, all right, which is just going to be 1.2 times 10 to the 4. Okay, so it's 2% less. And then the kinetic energy, okay, so going to part D. So then the new kinetic energy is going to be 1/2 m V final squared. Okay, and so that would just give us 1/2 times our 3,000 kilograms. All right, and then 1.2. I guess she has a small ship, huh? Meters. Oh, well, it was described as a shuttle. That makes sense. Okay, and there we go. And so that's 2.17 times 10 to the 11 joules. So 2.17 times 10 to the 11 joules. Now we could have found her kinetic energy before that, but now we're finding the kinetic energy afterwards. You'll see why. So in F, the mechanical energy of the craft, okay? So there should be a negative value, right? So this is going to give us the total energy. Let's see, because I'm going, let's see, I think I skipped E. Gravitational potential energy. So let's do that first. Okay, so E, that's just going to be, so U is going to be negative GM over R Okay, and we have everything there. So we got 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Mass of the world, 9.5 times 10 to the 25 kilograms. Mass of the ship, 3,000 kilograms. Right, divided by the radius of the orbit. Okay, 4.20 times 10 to the 7 meters, right? This is all stuff that we were given. We could have done this in the first place. And that gives us a potential energy of negative 4.53 times 10 to the 11 joules. Okay? And so then the total energy after the thrusters fire, make sure that was what we were asked. Yep. Yep. So this is after the firing. Okay. Because we didn't need to find the kinetic energy before the thrusters fired because it didn't come up in the problem. That's going to be K plus U. I think in the example in the or the problem in the lab worksheet, you kind of do because you have to compare between a circular and an elliptical. But here at least you're seeing a good part of the process. So we'll take the kinetic energy, or positive kinetic energy, times 10 to the 11 joules, positive 2.17, plus our potential energy, which is negative 4.53, and of course is larger in magnitude because we're in that gravitational potential energy well. And that gives us a total energy of negative 2.35 times 10 to the 11 joules. Okay. Great. And then we're going to go ahead and find the new elliptical semi-major axis. Okay? So then A is going to be GMM over 2 times the total energy. Now remember, I could have found R the same way. I could have found the total energy. Of course, that I could have used the velocity, or I could have used the radius to find it. I could have basically confirmed that we could have circled back around because we were given the radius, right? But this works for R as well, right? That there's no form. It's just there's no change in the form. It's just a different energy because of course our total energy has changed now that we've reduced the speed by 2%. Okay. And there we have. So we'll just plug in our values here. So 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times the mass of the planet, 9.5 times 10 to the 25 kilograms times our ship mass. Okay, and then we'll just divide by twice our total energy. So 2 times negative 2.35 times 10 to the 11 joules. All right. So, all right. And again, I'm just using these formulas, right? So, and that's why it's got to be a negative, because it's otherwise I get a negative semi-major axis. And so I've obviously this equation I've modified slightly just to solve for A, right? So I just cross multiplied by A, cross divided by E. Okay. All right, so now we're just solving for A. And so that gives us a semi-major axis of, let's see, 4.04 times 10 to the 7. So 4.04 times 10 to the 7 meters. How does that compare to our original one, right? Well, we see initially our circular orbit had a radius of 4.2. Our orbit now, our semi-major axis, is smaller. Right? So we have a smaller semi-major axis. We've reduced the orbit a little bit, made it a little bit more squished, a little bit more eccentric, elliptical in shape rather than circular, and a little bit tighter around the planet. Okay? So put a box around that. And then we want to solve for H, let's see. Yep. And yeah, so then we'll solve for H. That's just going to... Now, this one is I'm kind of going to use, or I said I was going to cheat and use Kepler's third law, because, we've used this relationship, right? This one between the period and the radius for circular orbits. Well, it turns out the exact same relationship holds for elliptic orbits. We just replace the R with an A. Okay, so then here, T for the elliptical orbit is just going to be the square root of 4 pi squared over gm a cubed. Okay, and those are all things we know now. We know a, we already knew g and m, of course. I'm going to not actually show the calculation this time, just to give you the number, but it ends up being 2.03 times 10 to the 4th seconds. And then finally, we're asked to compare them, which we can just look at the numbers. So in part I, which orbit has the smaller period? Well, when it was a circular orbit and it was going faster, it had a period of 2.15 times 10 to the 4 seconds. When it became elliptical, it lost energy. Its kind of orbital parameter distance-wise got smaller because it's again different shape, but its axis got reduced as it lost energy, and its period also got reduced. So that actually means it's going to make it around faster, right? It's actually going to get back to that same point sooner. Look at that. When it was circular, it took 2.15 times 10 to the 4 seconds. Now it's only taking 2.03 times 10 to the 4 seconds. So the elliptical orbit has the shorter period. So the elliptical orbit has shorter period. And that's kind of the crux of the question in the worksheet, is that by actually slowing down, okay, and the important thing is that the velocity that was firing a thruster straight forward, because if you fired it at a different angle, then you could just achieve a new circular orbit. But if you fire a thruster, you apply a force that is tangential to the trajectory, then you're going to then change your circular trajectory to an elliptical one. So a circular orbit to an elliptical orbit. And in doing so, you would actually reduce the period, so then you would get back to the same point faster than you would otherwise, which seems amazingly counterintuitive, but as you see, it works. And when you think about the energy, you actually see how it is working. Okay? So hopefully you find that interesting, and it helps you kind of see the process for solving the worksheet on your own. Okay, so thank you so much for watching, and please tune in for the